So far, you have studied a type of motion called translation, where an object can move in a straight or a curved line. So, it's time to spin things up a bit, and that takes us to the second type of motion that you'll study in this video lesson is rotation, where an object turns about an axis. Now, rotation can be a little tricky to understand, and therefore, in the first lesson, we will start by just defining the variables you will use when studying rotation. And what you'll find is that these variables are quite similar to those we use in linear motion, which will make things a lot easier for you to understand as we move forward. Also, do not get discouraged by a lot of Greek symbols that you'll see in this lesson. I can assure you that if you pay attention, this would turn out to be a very easy lesson. So here we take a rigid body that has some random shape and it rotates about a fixed axis that we call the axis of rotation. So you can see that the axis of rotation here is the z-axis, and here you have the x and y-axis that lie flat. So you're basically looking at the object from the top. Now, before we go ahead, we use the word rigid body to indicate that its shape does not change when it is rotating. So what I mean is, let us say you took a piece of jelly and tried to rotate it, you know for sure that its shape will change. So here we are dealing with bodies whose shape does not change, and therefore we call them rigid bodies. Now, if you observe a rotating body a little closely, you will realize that in pure rotation, every point of the body moves in a circle whose center lies on the axis of rotation. Also, every point moves through the same angle in a given time interval. So let us take two random points on this body, and what you will see is that if you rotate this point through an angle theta, this point would also move through an angle theta, and this would be true for every point on this body. That is, every point will move through an angle theta. Alright, with these basics in the background, let us work around the variables we will use while studying rotation, and we will also draw a parallel with their equivalent in linear motion. So the first one is the angular position of the body, which in linear motion is the position x on the number line. Well, to understand this, we'll draw a line on the body such that it is perpendicular to the rotation axis, and therefore rotating with the body. And we will say that the angular position of this line is the angle of the line relative to the positive direction of x-axis. So if the body is oriented such that this line lies along the x-axis, we say it is a zero angular position. And if we rotate the body by, let us say, 30 degrees, we say its position is 30 degrees. So you see, the angular position of the line is also defining the angular position of the object. And this is the way we define the position of the body at any given point of time in terms of angle theta. So here we can say that the angular position of this body is 30 degrees. Now, one thing you need to remember is that when dealing with rotation, we use radians instead of degrees for defining the angular position. So from geometry, we know that theta is written as s upon r, and this is what we call a radian measure. And here s is the length of the circular arc that extends from the x-axis, that is the zero angular position, to the reference line, and r is the radius of the circle. So radian is the ratio of these two lengths and therefore a pure number. As an example, a 180 degree arc would have an arc length of half the circumference, or pi r, and if you divide this arc length by r, what you get is the radian equivalent of 180 degrees, or pi radians. Likewise, if you move 360 degrees, your s value is nothing but the circumference itself, that is 2 pi r. And if we divide this by r, we get 2 pi. That is, we can say that the radian equivalent of 360 degrees is 2 pi radians. So this equality gives us 1 radian is equal to 57.3 degrees, which equals 0.159 revolutions. And you might want to memorize this because it will help you save time when you solve problems. Also, when dealing with rotation, we do not reset theta to 0 with each complete rotation of the reference line. And this basically means that if the reference line does 2 revolutions from the 0 angular position, we say that the new angular position theta of the line is 2 into 2 pi radians or 4 pi radians. So do not think that since this line has come back to this position, the new angular position is 0 radian. That would be incorrect. So if it does 5 revolutions, we say that the new angular position of the line is 5 into 2 pi or 10 pi radians. So now we will move on to angular displacement, and its equivalent in linear motion would be linear displacement. And this should be a lot easier to understand once you've understood angular position. So let us take the same body and rotate it about the axis of rotation and change its angular position from theta 1, which basically means our reference line makes an angle theta 1 with the x-axis, to angular position theta 2. Then we can say that the body has undergone an angular displacement delta theta, given as delta theta is equal to theta 2 minus theta 1, quite like we write x2 minus x1 for this. Also, you must remember that this expression for angular displacement holds not only for the body as a whole, but also for any particle that makes up the body. Because we discussed earlier, every point on this body moves through the same angle theta. The next variable we will study is angular velocity. So let us say the body is at an angular position theta 1 at time t1, and then sometime later at angular position theta 2 at time t2. We then define the average angular velocity. And by the way, why do we call it angular? Simply because there is angular movement of the body rather than linear. So the angular velocity of the body, that we will call omega, in the time interval t1 and t2 is given as omega average is equal to theta 2 minus theta 1 divided by t2 minus t1, which equals delta theta upon delta t. And you can see the numerator is angular displacement that happens in time delta t. Again, it is quite like the average velocity in linear motion, where the numerator is delta x instead. And the way we define instantaneous velocity in linear motion, that is by reducing the time interval delta t to 0, that is v is equal to limit of delta t tending to 0, delta x upon delta t, we do exactly the same thing over here. So the instantaneous angular velocity omega is the limit of this expression as delta t approaches 0, and this is nothing but d theta upon dt. So if we know the angular position, that is a function of time, we can find the angular velocity by taking its first differential with respect to time. So if the angular position is, let us say, given by the expression theta t is equal to 7 sine 3t plus pi by 2, then if we differentiate it, we get the expression for angular velocity, that here would be omega t is equal to 7 cos 3t plus pi by 2. So if you're asked what is angular velocity at t equal to 2 seconds, all you need to do is substitute 2 seconds for t in this expression. That'll give you the angular velocity of the body. Also, if you put t equal to 2 seconds here, you get the angular position. Again, both these equations hold not only for the rotating body as a whole, but for every particle of that body. Now, the unit of angular velocity we commonly use is radians per second, but often in problems you can also come across revolutions per second. Now, if you recall, for a particle in linear motion along the x-axis, the linear velocity v is termed positive if it moves in the positive x direction and negative if it moves in the negative. Quite the same way, we say the angular velocity omega of a rotating body is positive if it moves in counterclockwise direction, that is this, and negative if it moves clockwise. Also, remember the magnitude of angular velocity is called angular speed, which is also represented with omega. The next variable to study would be, and you probably guessed, the angular acceleration. And again, if we draw a parallel with linear motion, linear acceleration happens if the linear velocity is changing. Quite the same way, angular acceleration happens when the angular velocity of a rotating body is changing and is not constant. So let us say omega 2 and omega 1 are angular velocities at time t2 and t1 respectively. Then the average angular acceleration in the interval t1 to t2 is given as alpha average is equal to omega 2 minus omega 1 divided by t2 minus t1, that equals delta omega upon delta t. And direction of angular acceleration vector would be in the same direction as angular velocity when the body is speeding up, and in the opposite direction when it is slowing down, which makes complete sense since a body will speed up only if the acceleration is in the direction of velocity and slow down if it is in a direction opposite the velocity, quite like what you learned in linear motion. So here, delta omega is the change in angular velocity that happens during time interval delta t, and therefore the instantaneous acceleration alpha, which will come up most of the time in problems you come across, would be the limit of this expression as delta t approaches 0. That is nothing but d omega upon dt. And the unit of angular acceleration is radian per second square, or sometimes it could be revolutions per second square. Well, the next question that should come to your mind is, are the angular quantities vectors? And the answer is yes. So when we deal with a particle moving in a straight line, we can describe the position, velocity, and acceleration using vectors. But in straight line motion, we do not really need to describe vectors in I, j, k notation, since the particle has only two directions in which it can move, that is left or right, and that can be simply indicated using a plus or a minus sign. Now, if you take a rigid rotating body about a fixed axis, you can clearly see that it can rotate either clockwise or counterclockwise, and therefore we can again use plus or minus sign to give the motion a vector identity. However, we need to be a little careful representing the direction of angular velocity, which is vector omega pointing along the axis of rotation. And how do we establish whether it should be pointing up or down? Well, we do this by using the right hand rule. That is, you curl your right hand in the direction of rotating body. That is, your fingers should point in the direction of rotation. Then your extended thumb will point in the direction of angular velocity vector. Now, I know this might seem a bit strange. That is, this way of representing vectors is not the usual way. And in fact, it is a little difficult to comprehend at first because you're used to the idea of expecting that something should be moving along the direction of a vector. Well, it is different here because here the rigid body is rotating around the direction of the vector. So remember, when we talk about pure rotation, a vector defines the axis of rotation, not a direction in which something moves. Now comes the strange nature of rotation when we talk about angular displacement as a vector, and that is, it cannot be treated as a vector. And why so? Well, we can certainly give them both magnitude and direction quite the way we did for angular velocity vector. However, to be represented as a vector in the traditional form, a quantity should also follow the rules of vector addition. So, if you recall the lesson on vectors, if you add two vectors, the order in which you add does not matter. But you see, the angular displacement fails this test. And here is an example that will make it really clear. So, take a book that is initially horizontal and turn it by 90 degrees. First like this and then like this. So basically these are two angular displacements. Now let us go back to the initial position and give the same book two 90-degree angular displacements like this. That is, the first one is this and the second one is this. Now you see the two angular displacements are identical in both cases, that is 90 degrees, but the order is not. And what happens is, when you compare the final states, the book ends up having a different orientation depending on the way you flipped it. That is, angular displacement does not follow the commutative property of vector addition. So rotation is actually not as difficult as you might think, and it actually becomes quite simple when you draw an analogy with linear motion. And that is what we'll do in the next lesson. So if you like the lesson, do give a thumbs up and I will see you in the next lesson.